Alright, now chapter 12 part 1, where we are going to learn about static equilibrium. On previous topic, we've learned about the dynamic parts of the system. Whenever you have alpha of a system, angular acceleration, omega, and as well as AT, still remember? Alright, so that is on dynamic parts of a system. Means that where we consider the system having acceleration or motion. And now we are going to proceed into a static equilibrium. Okay, what does that mean by static equilibrium? Okay, the system has not gained any alpha or A, okay, throughout the process. Okay, so it means that the net external force on the object must equivalent to 0, because we know sum of F equivalent to MA, right? So if there is no A, then the F external just now is equivalent to 0. Not only in terms of translational motion or linear motion, in terms of angular as well, the alpha must be 0. Right? For this case, sum of torque equivalent to 0. Right? Because the alpha is 0. The angular acceleration is 0. Sum of the torque external on the system is equivalent to 0 because the alpha for the system is 0. Right? So if we refer to this diagram, undefined shape here, and we apply a force at point P, okay, where we have axis of rotation is actually at O. This is a pivot. So from point O to P, okay, this particle, okay, or section having R position, okay, from the pivot. And here is the vertical or perpendicular distance D, okay, from the line of action of the F applied to point P. So based on definition of torque is actually a cross product between position vector and applied force at that particular position. So in other words, this is equivalent to, if we're talking about magnitude of the torque, is magnitude of the R, magnitude of the F applied, sin theta. Okay, the smallest angle between them. Okay, and the unit is Newton meter. So talking about rigid object in equilibrium, sum of F external just now must equivalent to 0. It means that F in term of X, the net force in term of X, or the net force in term of Y must equivalent to 0. Okay, or if we consider up to Z-axis, sum of F in term of Z-axis as well must equivalent to 0. Right? And for the sum of the torque external equivalent to 0, okay, as we know, if the F and R within XY plane, the torque going to be in Z plane. You still remember the direction of it, right? The direction of alpha, the direction of omega will be on the third plane, which is on Z. So sum of torque for that particular system or object must also equivalent to 0 through Z-axis. So example of object in static equilibrium is this system. So if you refer to this, okay, the center of gravity of the system, combination between the bottle and the holder, okay, is directly over the support point. That is how we know that the object is in static equilibrium. Alright. So now, if we have more than one forces applied to our object, okay, bear in mind, talking about equilibrium, the A must equivalent to 0, sum of Fx equivalent to 0, sum of Fy equivalent to 0, alpha must be 0, sum of along Z-axis also going to be 0. So by make use of this information, we are going to calculate sum of F external on our system, mass equivalent to 0 along X and Y axis. Sum of torque external, okay, also going to be 0 for our system. Right. So we need more information on the center of the gravity. So since we are considering 3 parts, okay, within this undefined shape object, center of the mass for this shape of object must be determined first so that we know where going to be the center of the mass of it. How to calculate it? By using this formula, m1x1 plus m2x2 plus m3x3 up to n numbers of the particles over the total mass of the particles. In other words, we can simplify this equation into this, right? Then, to have the center of the gravity, okay, now center of gravity applies the same method actually. It's just that since we multiply with the G, this side also going to be multiplied with G. So we are going to have similar actually. Most of the time, center of the gravity is also center of the mass. Right. And at the center of the gravity is the where force due to the gravity acting on our object, or simply known as weight. Right. Now we move to example 8.8. Okay. Apply the condition of equilibrium and illustrate the use of different axes for calculating the net torque on an object. A woman of mass M equivalent to 55 kg sits on the left end of a seesaw, a plank of length L, which is 4 meter, pivoted in the middle as in figure 8.15. A. First compute the torques on the seesaw about an axis that passes through the pivot point. Where should a man of mass M equivalent to 75 kg sit if the system, which is a seesaw, plus man and woman, is to be balanced? Okay, remember we are in static equilibrium. Alright. B. Find the normal force exerted by the pivot if the plank has a mass of the plank equivalent to 12 kg. Repeat part A, but this time compute the torque about an axis through the left end of the plank. If we can visualize simple free body diagram of our plank just now with the weight of the woman, weight of the man, weight of the plank. Okay, so let's begin with sum of torque about 0.0 mass equivalent to 0. Right, so torque due to the normal and weight. Okay, here this is torque due to the weight of the man. The direction is clockwise direction. That is why I put it negative sign here. The torque due to the weight of the woman is counterclockwise direction. That is why it's positive. Right. So now, the weight of the woman times with the L. Okay. The L here is half of the total length of the plank. Okay. Here. Right. And the X is actually the position of the man to the pivot. X is here. Right? So it's negative because the direction is clockwise. And for the torque due to the normal, it's time no perpendicular distance, right? No perpendicular distance because it's acting on the pivot itself. That is why it's 0 here. Goes the same to the weight of the plank. So mass of the plank times with the G, but there is no perpendicular distance. Okay. Why is it here? There is no sine theta, there is no sine theta, sine 90 actually. Because it's already perpendicular. Right. So we are left with mg times with L over 2. Where is L? L is actually the whole length of the plank. Right. then minus mg mass of the man times with the g times x equivalent to 0. So from here we're going to solve for x, where we get 1.47 meter, okay, from the point O. Alright, for part B, okay, since the question asking for the normal force, we are going to use sum of Fy on the plank, okay, is equivalent to 0. So we have weight downward from the man, weight of the woman also downward, weight of the plank also downward, plus normal is upward, equivalent to 0. So from here, we will get our normal is 1.39 times 10 to the power of 3 Newton. Okay, for part C, we are going to calculate, okay, the top, okay. Now, our pivot is point O, which is at the left end of the plank. So, we have torque due to the weight of the man, which is clockwise direction, negative, m of the man times g, times with the perpendicular distance is the whole of this, from here to this, which is going to be L over 2 plus X. Right. Then we have weight of the woman. Yeah. Weight of the woman times, there is no perpendicular distance, times 0, because it's passing through the pivot or the axis of rotation. So it has no perpendicular distance. And what else? This is weight of the plank, okay, times G, M times M's plank of the other part. This is the weight of the plank times with L over 2. This is perpendicular distance from mass of the weight of the plank to the pivot here, plus normal. And for this one is also the direction is right, clockwise. That is why it's negative. But then for the normal, it's positive because the direction is according to the counterclockwise direction. Right. So the perpendicular distance from normal to pivot here is L over 2, mass equivalent to 0. From here we will get our X is 1.46 meter. What we can conclude here? Almost the same actually. Alright. Regardless actually which point we are going to take as the pivot or axis of rotation, still if the system is in equilibrium, we will get the same answer. Example 8.10. Okay. A uniform ladder 10 meter long and weighing 50 Newton rests against a frictionless vertical wall as in figure 8.17. A. Alright, if the ladder is just on the verge of slipping when it makes 50-degree angle with the ground, find the coefficient of static friction between the ladder and ground. Alright, so this is the physical diagram. This is a free body diagram. On the top here we have a push, okay, due to the touching here, a push from wall to the ladder. At the center of the ladder will be weight of it. At the touching point here, there is a normal and also friction. How we know that friction going to be in this direction? If the ladder is going to move, on the verge to move, the possible movement will be to the left like this, right? So friction will always be in opposite direction. Okay, for this case, as of now, it's static friction, right? So from here we have the free body diagram. Now the one that has many unknowns, okay, which is normal and friction is acting at point O. So it is the best point to become our pivot. Okay, it is not stated here, right? So it is up to us to choose which point to be the pivot. I suggest to you to select the point that you have as many as unknown, so that the torque due to that particular unknown will be 0 when we calculate sum of torque equivalent to 0. Right. So now we're going to choose point O as our pivot. Right. Then the possible rotation due to P is going to be like this, which is counterclockwise direction. And the possible rotation due to the 50 Newton in this direction, which is clockwise direction, which is going to give us negative. Before we start to calculate the torque, okay, let's analyze firstly sum of Fx equivalent to 0, because as we know, if the situation or the object in static equilibrium, all of the forces must equivalent to 0, as well as sum of torque equivalent to 0. So sum of Fx equivalent to, we have F to the right positive, we have P to the left minus P equivalent to 0. We know that friction is equivalent to P. Sum of Fy equivalent to 0. What Fy we have? We have normal, positive, and we have weight, downward, negative. Then from here we know that normal is equivalent to the weight of 50. Alright, now let's consider about the torque. Okay, the torque, sum of torque at point O as pivot must equivalent to 0. Okay, so what we don't have to consider the normal and the friction anymore, right? When we talk about torque at point O, because the normal and the force is passing through point O, so it has no perpendicular distance. Now we consider 50 Newton here. So we have 50 Newton, 5 times 5, because the total length of the ladder is 10. Okay, so if it is at the center, means that the distance from it to the pivot is 5. Alright, and then why is it cos 50 here? We want to figure out the perpendicular distance. Okay, the perpendicular distance of 50 Newton to pivot. Right. So sum of torque at point O is equivalent to 0. So the one that going to cause torque is 50 and also P. 50 Newton and also P. But then for 50, it has component, right? Because it has angle. So resolve the 50, you have this one is 50 cos theta, and the yellow one here is 50 sin theta. For the one that 50 cos theta, yes, there is torque produced due to that. But for 50 sin theta, if you can visualize it, okay, it's here as well, isn't it? So it's passing through the pivot or point O. That is why it has no perpendicular distance. So the torque produced by this one is 0. Okay, no need to consider. Yes, you have to calculate. And the tendency to rotate is clockwise direction for 50 cos theta. So we have negative 50 cos theta times with the length, okay, the D, which is half of the length of your ladder, which is 5. And it's negative because it's clockwise direction. Now for P as well, we have component of it. We have P sin theta and also P cos theta. But for P cos theta, similar analogy or method to that just now, if we can visualize it, we can transfer it here. So means that it's passing through the pivot or point O. It has no perpendicular distance as well. So the torque produced due to the P cos theta will be 0. But yes, we do have torque produced by P sin theta. And the D is the total length of the ladder itself, which is 10 meter. So all of these must equivalent to 0. From here, we're going to solve for P is equivalent to 21 Newton. Right. Now, to figure out the mu, okay, we are going to apply sum of Fx equivalent to 0. From here, we know that P equivalent to F, since we already have the information of P. And frictional force is equivalent to Fs maximum because the object on the verge on slipping, right? So mu s n, okay, so f itself or fs maximum just now is the p 21 here is equivalent to mu, the n is equivalent to 50 from where? From here, right? So you will know your mu is equivalent to 0.42. Example 8.11, okay, a uniform horizontal beam 5 meter long and weighing 300 Newton is attached to a wall by a pin connection that allows the beam to rotate. Its far end is supported by a cable that makes an angle of 53 degrees with the horizontal. If a person weighing 600 Newton stands 1.5 meter from the wall, okay, so find the magnitude of the tension T in the cable and the component of the force R exerted by the wall on the beam. So R can be visualized as the reactions. Okay, so this is a physical diagram. Now we are going to convert it into free body diagram. We have a reaction force, okay, this is just a lucky guess, okay, the direction of it. We are going to split it into components later on. So we have weight of the man, weight of the beam itself, and also tension having 53 degree from horizontal. Then in terms of R, now we put it in components ry and rx. Okay, so we don't have to consider the angle now because it's completely in component. Then you have this and you have this distance. Okay, t also resolve into components. So if we consider here point O here, okay, here as our pivot, okay, because it is pinned at this position, right? So torque due to the ry and rx are 0 because there is no perpendicular distance. Okay, the force itself, okay, acting on the pivot, right? So the torque due to the ry and rx is equivalent to 0, definitely. Goes the same to the t cos 53 because it's passing through the line of action of it, passing through the pivot. So there is no d or perpendicular distance as well. So the one that going to cause torque, okay, is t sine theta. The weight, this is counterclockwise direction. For the t here, it's counterclockwise direction. For the 300 Newton here, it's clockwise direction. For 600 Newton here, also clockwise direction. Alright. So now, okay, as I mentioned just now, no torque produced due to t cos 53, right? Okay, we are going to take sum of torque at point O equivalent to 0 because the whole system in equilibrium. So the torque due to the R, 0 because it's passing through the pivot itself. The torque due to the weight of the beam plus the torque due to the weight of the man plus the torque due to the tension equivalent to 0. So it's negative because it's clockwise. It's negative because it's clockwise. And the distance already perpendicular distance. So no need to put sine theta. Understood? So here you have, okay, 5 because it's the total length. Here you have 1.5 because of position of the man. Here you have 2.5 is at the middle. Alright, so from here, solve for the t, you will have your t for 13 Newton. Now, to figure out the r in terms of component, we are going to use sum of fx equivalent to max, but a is 0. So you have rx minus t cos 53 equivalent to 0. Then you will have rx equivalent to t cos 53, which give us 249 Newton. Substitute this one into this. Right, so we solve for rx. Now let's move to ry. Sum of fy equivalent to 0. We will have ry positive minus 600 pointing downward minus 300 because it's pointing downward plus it's pointing upward, t sine 53 equivalent to 0. So again, from here, calculate your Ry. It gives us 570 Newton. Let's take a look on example 12.3, the leaning ladder. A uniform ladder of length L rests against a smooth vertical wall. The mass of the ladder is m, and the coefficient of static friction between the ladder and the ground is 0.4. So in previous example, okay, this is the unknown to be solved. But now, this one given. Okay, the unknown is the theta. Find the minimum angle theta minimum at which the ladder does not slip. Okay. So this is a free body diagram of our ladder. We have normal, we have friction, because if the ladder going to slip, it's going to move into this direction. Then we have weight of the ladder at the center, and we have a push from the wall on the ladder. Right. Make use of summation of fx equivalent to 0. You will get P equivalent to Fs. Okay, make use sum of Fy equivalent to 0. You will have normal equivalent to weight. And bear in mind, to have P max is equivalent to Fs max, which equivalent to mu Sn, and n is equivalent to mg. Right. Now, let's calculate sum of torque at point O. Mass equivalent to 0 because the ladder is not moving yet, still in equilibrium. So what we'll have? We will have P times L sine theta. Okay, and the direction of the rotation is counterclockwise, so it's positive. But for the weight, the direction of the rotation or torque produced is clockwise direction, so it's negative. It's going to be mg times with the half of the length of the ladder cos theta, right? Because that is perpendicular to the ladder, right? So if we see here, you have sine theta, you have cos theta. Okay, we are going to somehow use tangent theta to simplify the sine and cos. So we are going to use sine theta over cos theta equivalent to tangent theta, where we are going to have mg, okay, over 2p, right? You make use of this actually. Let me show you. It's going to be PL sine theta is equivalent to mg L over 2 cos theta, right? So to have sine theta over cos theta, we are going to have mg L over 2 over PL. So L going to be cancelled out. Right. So that is how we are left with mg over 2p. Right. Whereby at the end of the day, theta is arctangent of mg over 2p. Okay. Our P is mu smg. So we can cancel out this. You have 2p, right? Okay, 1 over 2 mu s. And then finally we will get our theta is 51 degree. That's all for this topic. Thank you very much for watching. Do not hesitate to ask me any question regarding this lecture. Assalamualaikum.